Dear students, so in this lecture, I will discuss this dipole moment, something about dipole moment. See, this topic is more mathematical, more physical than, chemistry. So, very little chemistry is involved, only atoms are there. So, see how this, what is the property of molecule, this dipole moment. See, so far we have studied, broadly we can classify all types of molecule in three parts. One is like compound M plus and X minus, which is called ionic compounds, and they have some distance at some distance. This is you can say R in the lattice, and such type of compounds are said to be ionic compounds, right? Ionic compounds. They have, variable ionic character. Some ionic character is there, some covalent character is there. But overall, since ions are involved here, so we can say this is ionic compound, and electrostatic attraction is there in this ionic type of system, right? Ionic compound. Second category is where if we take some X and Y type of covalent compound, but this time the electron pair is shifted towards Y. So this is the electron pair. So when it is shifted, see here, this is complete charge, and now here there is a partial charge, delta positive, delta negative. So the bond is covalent, no complete ions are there. So such type of bonds are compounds in which such type of bonds are there are said to be polar covalent. Polar covalent. And third category, we can say that if we have X and X, so there is no net charge on because both the atoms are same, both have same electronegativity, so we can say this is non-polar. Non-polar, right? So because why this is non-polar, so you can very easily argue that the electronegativity of X is equal to the electronegativity of X, means both the atoms are same. So in this category you can see the example H2, right? You can have the example O2. In this category you have example like HCl, HF, like that. And here in this category you have example like NaCl, Na plus Cl minus. So broadly we have three kinds of molecules: ionic, polar covalent, non-polar covalent, right? Non-polar and covalent. Variable ionic character or covalent character are there. So if we consider this type of molecule or this type of molecule in which there is a clear cut dipoles, so mathematically we can define one term that is known as dipole moment. So there are two variables here. One is charge over these two atoms, and other is the distance. So in physics also you will find the definition of dipole. So dipole, basically dipole there is a scientific definition of dipole. See, you say dipole. Dipole is an arrangement of oppositely charged ions. If two oppositely charged ions were kept at a very short distance, then this arrangement is called dipole, right? So this is the simple definition. So dipole is nothing but it is the arrangement 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 in which two oppositely charged ions are kept at very short distance. Very short distance. So here we can say interatomic or ionic distance. So if two oppositely charged ions were kept a very short distance, you can say interatomic or interionic distance, then this is called dipole, right? And what is the moment? Basically, when this dipole, if you see, if you apply an electric field, suppose that in this direction, if you apply this electric field, and suppose that if you put a dipole here, this is a dipole, a positive or negative charge. See here, in this definition, it is not said, okay, that I mean there should be this amount of charge. Amount of charge could be anything. So if you put such molecule in electric field or such arrangement electric field, this will feels the force of attraction and force of repulsion with the external magnetic field, and this will show the movement in external magnetic field. So this is called what? Dipole moment. There is a torque will apply on this, and this dipole will try to arrange themselves in such a manner that this will have the minimum energy, right? So this is the concept of this dipole moment. So how it is defined, how much interaction this showing with the external magnetic field. So such arrangements or such systems, we can say, means this is the system. So such systems shows interaction with external electric or magnetic field, right? So this is the, I mean, characteristic property of any molecule. If any molecule shows this interaction in the electric field or magnetic field, so we can say, okay, this molecule have some kind of what? Dipole. Less or more, that is a different issue. Now see how it is defined. So suppose that if we take A, B, so first you have to write the feature of this molecule, AB molecule. This is covalently bonded molecule. Covalent bond is there. How many bonds are there? Only one bond. Only one bond is there. And we are assuming that the electronegativity of B is more than the electronegativity of A. So there is delta negative charge and there is delta positive charge, right? So and let the internuclear distance is R angstrom, because you know bond lengths basically this is the internuclear distance between A and B. So bond length is in the order of what angstrom. So dipole moment, basically it is defined as mu, it is represented by mu, it is defined as the magnitude of charge. Don't take positive or negative, whatsoever magnitude, see, this is equal and opposite charges. See, arrangement in which two oppositely charged equal, we can add here equal and opposite, equal and oppositely charged, equal and oppositely. So you should take the magnitude of charge here into internuclear distance r. This is I have taken in angstrom. So this dipole moment is given by this equation, equation 1, where this mu is called dipole moment of bond oblique molecule. Why? Because in this case only one bond is there in the molecule, so this is the dipole moment of the bond as well as of the molecule. Okay. So see, this dipole moment, it is a vector quantity basically. So dipole moment, what is the feature of this? Dipole moment is a vector quantity. Vector quantity. So means it has magnitude as well as the direction. So what is the normal direction of this dipole moment? So this is very, very important point here. The direction, the direction of dipole moment is from less electronegative atom to more electronegative. So this is the concept basically. So here this is more electronegative, this is less electronegative, so the direction is this, right? Direction is this. So now see, if we take here unit positive and unit, although this is not a unit positive and unit negative charge is there, but if we consider this unit charge, so one unit charge, if we consider here one unit charge into R, so R we can take 1 angstrom, right? So here I have taken charge 1 unit and distance, internuclear distance 1 angstrom. So if we take in CGS system, so what is the magnitude of charge in the CGS system? The magnitude of charge is 4.8 into 10 to the power minus 10 ESU. ESU, electrostatic unit, this is the unit of charge in CGS system, and 1 angstrom is equal to 10 power minus 8 centimeter. So you can say 4.8 into 10 to the power minus 18 ESU into centimeter, right? ESU into centimeter. Now see, this is equal to, you can write here, is equal to 4.8 dBi. 4.8 dBi, right? Or you can write 4.8 D, capital D. So dBi is the unit of dipole moment. Unit of dipole moment. right? D by. And 1 d by is equal to, you can write 1 d by is equal to 1 d by is equal to 1.0 into 10 power minus 18 ESU into centimeter, right? So this if the charge, magnitude of charge is 1 unit and the internuclear distance is 1 angstrom, so the dipole moment of that bond is 4.8 d by. So hopefully all of you are clear how to calculate this dipole moment. And if you want, you can make the relation between d by. See, this is the standard unit of dipole moment. But if you want, you can convert this into coulombs, meter, and other units. So I am directly writing here 1.6 into 10 to the power minus 29 coulombs. If we take here unit charge in coulombs and this is in meters, so coulombs into meters is equal to 4.8 d by 4.8 d, right? So if you take here 1.6 into 10 power minus 19 and here 1 meter, so see 1 angstrom, so this is 10 power minus 10 meters, so this equal to 10 power minus 1. So this equal to, you can write 4.8 d by. So 1 d by is equal to you can write 1.6 into 10 power minus 29 by 4.8, right? This is coulombs into meter, and so this is equal to what? 3.336 into 10 to the power minus 30 coulombs into meter. So this you can write, right? So this is calculation of bond moment, right? Okay. See, suppose that if in any molecule more than one polar bonds are present, right? If a molecule has have more than one covalent bond or more than one polar bonds. Then the dipole moment of molecule is given by the vector sum of bond dipole moments. Right? So this is very important point, and all of you are knowing that if how to find the vector sum. All of you gone through in physics this calculation. So I mean, I think you have no problem to calculate the vector sum, but I am giving you the formula. Suppose that two vector of suppose that the angle between them is theta. So mu1 and mu2, two vectors are there. So the resultant of this is given by mu r is equal to under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, right? So by this equation, using this equation, you can calculate the resultant dipole moment, right? So if a molecule has such I mean vectors, more than one such vectors, then this is the vector sum. Dipole moment is the vector sum of all such dipole or bond moments. And if mu1 is equal to mu2, let it is equal to mu. So equation 1 you can reduce mu r is equal to 2 mu cos theta by 2. So this is equation 2. This is I mean mathematics. Now all of you are from mathematics background, and all of you are knowing this formula. You can reduce this, put here mu square plus 2 mu square cos theta. So you will get this formula, right? So mu r is equal to 2 mu cos theta by 2. And one more point here we can put note that if three or more than three vectors of equal magnitude are oriented at the equal angle, then the resultant is always equal to 0, right? If vector of, if two or more vectors, if two or more vectors with same magnitude, same magnitude are oriented at same angle, same angle from each other, then mu r is equal to 0. The resultant dipole moment is 0, right? Suppose that two vectors of the same magnitude, they are oriented 180 degree from each other, 180 degree, right? Suppose that this is mu and this is also mu. So mu r is equal to 0. Suppose that three vectors are oriented at 120 degree from each other and all have same magnitude mu. So how to calculate the resultant? In physics you have learned about how to calculate the addition of multi vectors. See, resultant of these two going to like this resultant, so that is cancelled by this. This resultant of these two cancelled by this, resultant of this cancelled by this. I am not going to that, and I can say the mu r is equal to 0 for this. Similarly, if four vectors like of same magnitude like 109 degree 28 minute if they are oriented like this. So mu all have magnitude mu, right? Mu. So mu r is equal to 0. Mu r is equal to 0, right? So if in any molecule, right, equal magnitude vectors are oriented at equal angle, then the resultant dipole moment of that molecule, overall resultant dipole moment is 0. So this is the, I mean, calculation and what resultant dipole moment and as well as the bond moment of, okay, any molecule. See, so Q into R, this formula you should use to calculate the bond moment, and vector formula you should use the resultant dipole moment of the molecule, right? And if any molecule have only one bond, then that is the bond moment as well as the dipole moment, right? And now we can see in different geometries like in in this geometry, if it is asked that in PVP geometry, see these three vectors are at the same angle, and these two vectors are at the same angle. So what will happen? What is the resultant of this dipole moment? See, this is kind of the resultant of this and this. See, this is 0 and resultant of these three is 0. So you can say, although here different magnitude you can say of dipoles we have, because this R of this and this is same, but R of this and this is not same. But although mu R is equal to 0, because in this case we have to find out the dipole moment, resultant dipole moment in two sets, one for this and one for these three. So these three, this is 120 degree and these two, this is 180 degree. So in this way you can find in the resultant dipole moment of this molecule in two parts, one for axial bonds, one for equatorial bonds. So you will get the final resultant dipole moment of this molecule. Now see one question here. Calculate the dipole moment of HCl. So first you have to draw the structure of HCl. This is delta negative, this is delta positive. If the equilibrium bond length, why the word used equilibrium bond length? You know the atoms are always in the vibrational motion in every molecule. This bond is not static. These atoms are always continuously through and fro motion. So the equilibrium distance is always constant. So that's why the word equilibrium bond length is used here, 1.2746 angstrom, right? And what is the magnitude of charge? 1 unit magnitude of charge plus 1 minus 1 here. So the dipole moment, and what is the direction of this dipole moment? From here to here, and only one bond is there. So we have to calculate this. This is del mu is equal to 1 unit charge into internuclear distance, 1.2746 angstrom. Just simple calculation, nothing else. So what magnitude we can put here, and it is default. If nothing is given, then you have to calculate in dBi. So 4.8 into 10 to the power minus 10 ESU into 1.2746 into 10 to the power minus 8 centimeter, right? So this you can write here 4.8 multiplied by 1.2746 into 10 to the power minus 18 ESU into centimeter. So this you can write 4.8 into 1.2746. This is equal to, I think it is 5.99. 5.99 and 1.0 into 10 power minus 18 ESU into centimeter is equal to dBi. So this is 5.99 dBi, right? So this is answer. So in this way, simply you can calculate, as we know that 1.0 into 10 to the power minus 18 ESU into centimeter is equal to 1 dBi, right? So this is simple question. Now see another question. Mu resultant of water is 1.85 dBi, ignoring lone pairs, contribution of lone pair. So as we know the structure of water molecule, so you have to write like this now, because now all of you are aware of the structure of this. So these are the two lone pairs. So see, this is delta positive, this is delta positive, and this is delta negative, right? So the direction of the dipole is this. This bond dipole is this. Right? From less electronegative to more electronegative. And the lone pairs, the direction of lone pairs like this. But here I am not going to consider the lone pair dipole direction. So what should be the resultant of these two? Definitely resultant of these two you will get like this, right? And this is given. This is given. So mu r is given here 1.85 dBi, right? Of these two bonds. So what they have asked, dipole moment of each OH bond, right? So let the dipole moment of this bond is mu, and this is also mu. Why? Because both are OH bonds, have same polarity, same atom. So this is same. So what we can see here, what we can write, mu r is equal to 2 mu cos theta by 2, right? Cos theta by 2. So mu r is given. Mu r is what? 1.85 dBi is equal to 2 mu, we have to calculate, and cos theta 104 by 2. So this is equal to 2 mu and what? Cos 104 by 2. So this is cos 52. degree. So now see, this mu is equal to cos 52 degree is equal to, I think it is 0.61, 52, 52, 52, 0.61. So cos 52, cos 52 is equal to 0.61. So we can write here mu is basically here the bond dipole of OH bond. This is equal to 1.85 divided by 2 into 0.61. So you will get 1.5 dBi. So this is the answer, right? So in this way you can calculate the individual bond moments. So this is called a bond dipole. This is called bond dipole. So hopefully all of you are clear in this calculation that what is resultant dipole moment and what is the dipole moment of molecule and what is the bond dipole, right? Now see the application of dipole moment. So the application, we have various application of this dipole moment. So one is polarity of molecule. See, polarity of molecule, this the best way to explain the polarity of molecule is the resultant dipole moment. See, if mu r is equal to 0, then the molecule is non-polar. And if mu r is not equal to 0, then the molecule is polar, right? So see, suppose that if a molecule has polar bonds, so it is not necessary that overall molecule is polar. See, presence of polar bond. So we can write here that the presence of polar bonds is necessary for polarity of molecule, but not sufficient. That is means if polar bonds are there, then it is not necessary that molecule is always polar, right? Because the mere presence of polar bonds will not ensure that the molecule is polar, right? Now we can see different examples of this, that how this can be justified. See, if you see carbon dioxide molecule, so with the help of hybridization and everything, VSEPR model, every model, you have the fine structure. If you have drawn incorrect structure of this molecule, you will have the incorrect conclusion. So by applying all those concepts of bonding which we have already gone through, you have to make the structure of that molecule. So this is the perfect structure of carbon dioxide molecule. This is not the structure of carbon dioxide molecule. This is not the structure of carbon dioxide molecule. If you draw the structure of carbon dioxide molecule is this, you will have the different properties of this molecule, and that obviously that is incorrect property, right? Now see this carbon dioxide molecule, how the bond dipole. So see, uh, this is less electronegative, this is more electronegative, this is delta negative, this is delta positive. So this is one vector and this is another vector. And what is the angle between these two? 180 degree. What is the magnitude of so here polar bonds in this molecule, polar bonds, the answer is yes. In this molecule polar bonds are there. So if mu is the dipole moment of this bond and mu is the dipole moment of this bond, so what is the mu r? So mu r is equal to 0. And if mu r is equal to 0, then the molecule is overall non-polar. So polar bonds as molecule is polar. The answer is no. Why? Why? The answer is because the mu r is equal to 0. So basically mu r will determine whether the molecule is polar or non-polar, right? So see, this molecule is non-polar. Similarly, if you see BF3 molecule, if you have so see BF3 molecule, 3 bonds, sp2 hybridized. If you are not able to draw the perfect structure, you cannot predict the dipole moment. So 120 degree, bond angle is 120 degree, 3 vectors oriented at same angle from each other. So mu r is equal to 0. Mu r is equal to 0. Polar bonds, the answer is yes. Polar bonds, yes. Molecule is non-polar. Molecule non-polar. So for molecular polarity, you have to see the resultant dipole moment, right? Similarly, if you see PCl5 molecule, so now this is homework. All of you should draw the structure and find the mu r for this. CCl4 molecule, for all these the mu r is 0. So draw the structure, perfect structure showing the different vectors, right? So mu r is equal to 0. Therefore these molecules are non-polar, right? So in this way you can find out whether the molecule is polar or non-polar by using this dipole moment. Now see the percent ionic character. See the percent ionic character. This is the second application. Percent ionic character. So percent ionic character you can calculate by using different formula on the basis of this dipole moment. So percent ionic character is equal to mu experimental divided by r observed by mu calculated into 100. And you know mu calculated is always greater than mu observed, right? So this is one method to calculate this percent ionic character. This is one method to calculate the percent ionic character if you have dipole moment. So percent mu, observed by mu calculated. Another formula I have already told you, but here you can revise this. The percent ionic character, percent ionic character is equal to 16 xb plus 3.5 xb square. So this is another formula for the calculation of percent ionic character, right? So these two formula you can use. One more formula is there, that is called Pauling's formula, and that percent ionic character is equal to 18 mod of XA and XB are the electronegativity power 1.4, right? So this you can use. This is also you can use the formula. This is called Pauling formula. Pauling's method, and this is, I think, Henry and Smith. Henry and Smith. Smith, right? So these are the formulas by which you can calculate the percent ionic character in any molecule, right? Now see, this is one question. For HCl molecule, it is given mu. Observe this. So for HCl molecule, delta positive, delta negative. See, this is, so mu observed, it is given 1.03 dBi, and we have already calculated for this 1 unit charge multiplied by 1.275 Armstrong. So this we have calculated in the previous question. See here, see 5.99 dBi, right? 5.99 dBi. So mu calculated is 5.99 dBi. So percent ionic character is equal to mu observed by mu calculated into 100. So this is equal to 1.03 by 5.99 into 100. So 1.03 divided by 5.99. So this is equal to 17.1. So this is equal to 17.1%. So in HCl molecule, 17.1% is the ionic character. So covalent character is equal to 100 minus 17.1. Right? So this is how much? 18, 83%. So it means HCl molecule is covalent. This bond is covalent, not ionic, right? And see this ionic character 17%. So you can say, okay, polar covalent character is there, right?